This episode is supported by 23andMe. If you study a map of the cosmic microwave background, or CMB, you may notice a large deep blue splotch on the lower right. This is the cold spot. Is this feature a statistical fluke, the signature of vast supervoids, or even the imprint of another universe? Is that giant cold spot in the cosmic microwave background really evidence of a collision with another universe? That's what all the media hype is saying, which means it's time for another Space-Time Journal Club to sort it out. Today we're going to talk about a fascinating new publication by Mackenzie et al. 2017 titled Evidence Against a Supervoid Causing the CMB Cold Spot. First, the name. Evidence against a supervoid. The leading explanation for the cold spot was that it was imprinted on the cosmic microwave background radiation as that radiation passed through giant empty regions of the universe, so-called supervoids. The evidence against part tells us that the authors think that this hypothesis is wrong. This is partly what excited everyone about the alternative bubble universe collision hypothesis. Before we go into detail about either of these hypotheses, let's get the basics down. The cosmic microwave background is everywhere. It's the light that was released at the moment that the first atoms formed, 380,000 years after the Big Bang. For all of the gory details, check out our previous episode. The CMB is amazingly uniform. When it formed in the early hot universe, it was mostly infrared light with a temperature of 3000 Kelvin. 13.5 billion years of cosmic expansion later, and it's stretched to microwave wavelengths, and to a temperature of very close to 2.725 Kelvin all across the sky. Although it's very smooth, the CMB does show lots of very tiny fluctuations in temperature. Those are all of those smaller blotchy spots. We think that they came from random quantum fluctuations from the very first instant after the Big Bang. These were then amplified by a period of exponential expansion in the very early universe that we call inflation. The typical deviation from the average temperature is around 20 microkelvin, so the differences are 1 part in 100,000. The cold spot, which is in the direction of the southern constellation Eridanus, is 150 microkelvin cooler than the average. It's also huge, 10 degrees across for the coldest patch, with a less extreme halo and hot rim that's 20 degrees across. Think 40 full moons. Now, it's possible to explain the cold spot as just an unusually strong random fluctuation in the CMB. Just like those small blotches, but by chance, very large. Simulations show that you should get a spot that size in the CMB in around 1 in 50 universes. So we might be in one of those slightly rarer universes with a big CMB splotch. Really, in any given universe, there should be a few weird 1 in 50 things, but the odds are low enough that it's worth investigating. Inu and Silk in 2006 first proposed the cold spot could be the imprint of a supervoid via the so-called integrated Sachs-Wolf or ISW effect. The ISW effect is dark energy in action. It's a cosmological tug-of-war. Gravity pulls things in, while dark energy pushes things out. A photon entering a matter-rich galaxy cluster gets an energy boost as it falls into the cluster's gravitational well. But by the time the photon is on its way out, the expansion of the universe has actually stretched out the cluster, weakening its gravitational pull. There's a steep slope down and a shallow slope up, just like a ski ramp. The photon exits with a net energy gain, which would register as a higher temperature on our CMB map. But the opposite happens when a photon enters a void. It loses energy going in because it's being pulled backwards by the higher density universe behind it. but the galaxies have spread a little further out as it exits the void, so it doesn't get pulled out as strongly. The ISW effect would be tiny, in fact negligible, in a universe without dark energy. The difference between the going in and going out boosts would be so small that they wouldn't be noticed. But around 4 billion years ago, dark energy caused the expansion of our universe to begin accelerating, whereas previously it had been slowing down due to gravity. In an accelerating universe, the difference in the ingoing and outgoing boosts can be large enough to be detected. So if there are giant voids in the direction of the cold spot, then these could have sapped energy from the CMB photons as they passed through. Mackenzie et al. Used the Anglo-Australian telescope in outback New South Wales to perform a spectroscopic survey of 7,000 galaxies in the direction of the cold spot and out to a redshift of 0.4. Or, in layman's terms, they split the light from those galaxies into component wavelengths and determined the shift in the wavelengths of those spectra due to the expansion of the universe, i.e., they measured redshifts. This gave distances to those galaxies which ultimately allowed them to build an accurate 3D atlas of galaxies in the direction of the cold spot, all the way out to the point where dark energy started to dominate the universe. They found 3, maybe 4 supervoids. However, the combined ISW effect they calculated from all 4 voids should only have produced 32 microkelvins of reduction in temperature in the CMB, which is a mere fifth of the observed 150 microkelvin drop. Mackenzie et al. Also observed a control region, G23, in the direction of the star Fomalhaut. G23 has a similar void structure to the cold spot's line of sight, plus a couple of overdensities. G23's ISW effect is calculated to yield a 14 microkelvin drop in the CMB. And that's actually a good match to the observed deviation of 15 microkelvins. So the control sample shows that calculating the ISW effect can lead to a number that matches the true effect. Mackenzie et al. Conclude that this means supervoids can't be the sole explanation for the 150 microkelvin cold spot. What is it then? Well, there's a good chance it's actually just a statistical blip. The void hypothesis was always the least crazy idea. But now that seems to be ruled out, it's at least worth talking about the more crazy notions. First, there's the ever-recurring idea that gravity is wrong. It's the same notion that people have tried to use to explain dark matter. Basically, the idea is that the calculation of the ISW effect, the effect of the voids, is lower than expected because we don't understand gravity on large scales. However, modified gravity is on shaky grounds because, well, dark matter is looking more and more like real stuff, not incorrect gravity. Also, the control field gave roughly the right answer, which it shouldn't have if our understanding of gravity was so far off. The other weird ideas are about what happened in the inflationary era. There are ideas like the amplification of topological defects in the universe, or an inhomogeneous reheating at the end of a non-standard inflation. But the one that gets most people most excited is, of course, that the cold spot is the mark left due to a collision with another universe. So what's that all about? A popular version of inflation theory is that of eternal inflation. The idea is that the initial period of exponential expansion that we call inflation actually lasts forever. It's a whole big topic, and we'll do an episode on it at some point, but in eternal inflation scenario, a normal universe begins when a small patch of the inflating universe stabilizes. In particular, its vacuum energy takes on a stable value. At that point, it stops inflating and starts expanding normally. This can happen spontaneously anywhere in the greater inflating space-time, resulting in bubble universes. And it can happen frequently or rarely depending on the completely unknown details of the string theory parameter space. But regardless, in an infinitely inflating space-time, collisions between bubble universes are eventually expected. So what happens when two bubble universes collide? Well, they merge and exchange an enormous amount of energy. Chang, Klebert and Levi, 2009, figured out that this should result in a temperature gradient across each universe. If that merger point is distant from us, then this looks like a hot or cold spot in the cosmic microwave background. The colliding multiverse explanation is still pretty fringe. Mackenzie et al. Have debunked the more standard explanation of the cold spot, and so multiverses are still in the running. If real, this would be the first piece of evidence that a universe beyond our own exists. However, more detailed observations of the CMB in that region are needed to rule out it being a statistical fluke, which honestly it probably is. But if not, perhaps once upon a time we really did collide with an entirely separate bubble of space-time. Thanks to 23andMe for sponsoring this episode. The name 23andMe comes from the fact that human DNA is organized into 23 pairs of chromosomes. 23andMe is a personal genetic analysis company created to help people understand their DNA. You'll be able to see which regions around the world your ancestors come from, understand how DNA impacts your health, and learn how your DNA influences your facial features, hair, sense of taste and smell, and sleep quality.